All right, so good morning, everyone. Welcome to today's lecture. Can I have your attention back? All right. Let's continue with example 23, which is a little bit different with the previous examples. We have a mass that moves up and down, but this time we cannot ignore its size, so it also can rotate. It has actually 2 degrees of freedom, and that's your example 23. It gets you one step closer to know how to solve your course project, which is actually a very simple example, but important in the realm of vibrations. So the center line of this bar, let's say if I assume it as one line, that line can obviously has 1 degree of freedom, can move up and down. Let's say I assume that center line moving up in that direction, and since everything is symmetric, I can assume that like the center of gravity, G is in the middle. So that's G, and this G moves up by my variable. I can call it X. Right, so that center line of this bar can move up and down with the variable X. Again, I emphasize it's up to you. You can choose X downward. There is no difference, but you have to be consistent and stick to it. Now that we show it X going up, it means that's the positive direction. So when I'm writing the equation, any force in that direction is positive, any other force in opposite is negative. So you know the drill. So, and then this line at that point, it has also another degree of freedom. It can rotate. Right? So my second, let's say I can show it there. Variable will be theta. So I call this angle theta. So as you can see, this is my decision. I decide to rotate it like that one. Okay, so you could rotate it the opposite direction. There is no limitation for that. Okay, so the center point moves up by X and rotate by theta. The first step, we know we need to draw the free body diagrams. And since it is vibration, I can assume the the changes is not that much, so cosine theta is almost equal to 1. But to get a better sense, let's show it in that angle so we know what we are discussing. All right, so this bar moves up. The forces that I have acting on the two sides, there are the stiffness forces and there are the damping forces. So the stiffness and the damping. I want to use the different colors so we can distinguish them. So let's use this guy. And we assume these two are very close to each other. So my forces for each side, on the left side for the spring, I know it is K1 multiplied by the amount that it has been deflected, okay? So if I look at that point, K1, it moves up by X, and then it was compressed by L/2 theta. So I make an assumption that X is bigger than half of L theta, so my force then will be tension, and I show it like that one. If I know the force for stiffness, the damping is very similar, except it is velocity. X dot half of L theta dot. And with the same logic, on the other side, we have K2. And I have X, right? X, the amount that elongate this spring, and then theta, which add to that one, plus half of L over theta. And the damping will be then C2 X dot plus L/2 theta dot. This is my free body diagram, and if I get this one right, the rest just coming along with no problem, right? So that's the center of gravity for these things. And this was the horizontal line that we set as a reference. Okay, so again, for this sort of problems, you need to check the free body diagram. It can move ups and down, and it can rotate. Assume one positive direction. It can be anything. You can show it coming down and rotate clockwise. Doesn't matter. So, but all matters is that we know this direction is what we choose as positive, and also moving up is what we choose as positive in this problem. The opposite one, if you choose, that's okay. So I have a rigid body. It's not a particle. I need to use Euler equations. So remember Euler's equation for rigid bodies, we have two scenarios. One being fixed to a point. This is not that case, right? There is no pin or anything being fixed to that point. So we are limited to taking the moment about only center of gravity, which is equal to I bar theta double dot. That's our Euler's equations. So we know how to take the moment about point G, and we know I bar for a bar, right? I'm going to write it down if you forget, but one of those things that you should remember, 1/12 mL squared. And the second equation that I have is some of the force in X direction is mx double dot. So you know how to write these equations. I'm not going to waste time on that. And if you write the equations, summarize everything, so you will get, I got the summary here. You will get m0, 0, 1/6 ml x dot theta double dot. And then for C, you will have C1, C2 minus C1, C2 L/2, C1, C2 L/2, and this guy will be C1 plus C2 multiplied by L over 2. That's my damping matrix, X dot theta dot. So if you're writing notes, you need to be a little bit frugal spending space here in this problem. Next year, maybe I should have 2 pages for this one. That's why I divided my slide to half. And then we will have another piece. This one smaller then. I can do that. Hopefully you can do that on your own. And then I have the K matrix, K1, K2, minus K1, K2, L over 2, minus K1 plus K2. This one doesn't have L over 2. Please correct damping matrix. And this one is K1 plus K2, L over 2. That's correct. Some rooms. And I have X and theta equal to 0. So that's my equations of motion for this system, which please try to write the equation, simplify it, you will get to the same matrix, hopefully, if I haven't done any mistake. Yes. So the K matrix, which part? You mean here? No, there is not. But that's a good point. Usually they are symmetric, but this one, the nature of X and theta, they are different. X is linear, theta is rotation. That's why one of them doesn't have L over 2. And please write one of these. When I simplified, I made a few mistakes when I wrote them. So it's good practice, good practice to do this.
Will be always rotating around center of gravity?
No, I'll get to that one shortly. If it is around center of gravity, then that's a good thing, but doesn't have to be around center of gravity. So that's in fact a good question. If your center of gravity is somewhere that the distance is A and B, you will do the same things. But remember the Euler law, always you have to take the moment either about center of gravity or about the point that the whole thing is being fixed and joined. The reason that you do the, which I explained when, like in early lectures, we do the moment about the center of gravity because we want to get rid of the MA. There is an acceleration at the center. So this is the equation. We know what to do with it. We know in order to solve this one, right, we need to go through all the trouble of decoupling and so on, which all those steps that you've seen before. Which you can do that one, however, it's not what the question asks. The question asks, check what will happen is the stiffness and damping, they are the same. So let's say my stiffness are equal to K and my dampings are equal to C. So I have a special case if K1 is equal to K2 equal to K and C1 is equal to C2 equal to C. So if we simplify the matrices, we will get M0, 0, 1 over 6 ML, X double dot, theta double dot. My damping matrix will be 2C, 0, 0, and CL, right? 2CL, X dot, theta dot, the stiffness 2K, 0, 0, and KL, X theta equal to 0. Right? So looking at these new matrices now, I realize actually they are decoupled. So the mass matrix is decoupled. It was before as well. The stiffness, the damping and the stiffness, they're all decoupled. They are all zero. So zero. So for this special case, then my system is decoupled without we do anything. Okay. I'll give you a moment to take notes and then we'll see what we need to do with that. Yes, please. Oh, you're right. Thanks for reminding me. So please correct that one. Something not right with me today. I'm making mistakes, even from my own notes. K1 minus K2. Yeah, now it's correct. Okay, please correct this one. This is C1 minus C2 and K1 minus K2. And always please go home and check my calculations. Okay, I'll do them quickly and I might have made mistakes somewhere. So now let's focus on this scenario. Okay, this is a special case. We have a symmetric system and without doing anything, without decoupling the system itself is decoupled. What is the physical interpretation? So when I have this scenario, it means I have two independent equations. Let's write them not in a matrix format, in a regular format. So I'll have mx double dot plus 2cx dot plus 2kx equal to 0. And over here I have 1/6 ml theta double dot, or I can get even rid of L. Let's just leave it. Half over 6m theta double dot c theta dot plus k theta equal to 0. Yes, all right. So looking at these two equations, immediately we realize two independent equations, right? X and theta have nothing to do with each other. If they have nothing to do with each other in differential equation, it means when they do the motion, they are also independent. Okay, here is the physical interpretation of that. Physical interpretation. So we say we have two modes. Mode number one let me draw it. So this is K, this is K. My center of gravity is in the middle. Cannot see it. And these things only moves ups and down. I have only one variable. Yes, please. So the equation for I bar is 1/12 ml squared, right? Probably I simplified everything by two factors. Okay. So, but again, please go and check to make sure it is 1/6. Yes, please. we can, but it's very difficult when we involve rotation and linear translation at the same time. Yeah. So that's a good point. Remember, we could check the add of springs and the add of damping for diagonal or off diagonal. We can do it here. However, I don't because it's difficult to explain when it involves rotation and translation. Okay. So let's look at these two modes separately. Mode 1 is the system only moves ups and down. The proof is here because my equations tells me that there is no theta. It's only x. So if I have this system that moves ups and down, it means I have the natural frequency for this system, which is simply 2k over n, right? Because my stiffness is k plus k, 2k. This system has only 1 degree of freedom, and we know how to solve it. And my equations also show the same thing. What is my mode 2? Mode 2, it's only rotation, pure rotation. So let me draw that things. And this is my center of gravity. And I only have pure rotation. So I have the springs. Again, they're going to be k, and my variable is theta. Okay. So it is pure rotation about G. Mode 1 is pure translation. So if it is pure rotation, yes, please.
Is there any?
Oh, we have also the damping, but since I'm just discussing the stiffness, I didn't want to make the picture messy. But the damping stay there. We have damping here, we have damping there. So remember when we discussed the natural frequencies and mode shapes, we only care about the stiffness. So my mode 2 is pure rotation, and I can solve a problem which is pure rotation. So when I say pure rotation about G, you can assume that R is joint or joint, yes, joint to the screen. So you can assume that point G, that's G, right? Because it's pure rotation, it can spin about point G. That's all. Point G doesn't move ups and down. Why? Because our equations prove that there is no x in our equations, right? It is only theta. If it is only theta, it means x is 0, so it doesn't go ups and down, it's only rotate. So here is then the physical interpretation of this system. If I have some conditions, the two modes in this system, they will be decoupled. And it happened only for this specific scenario. But let's have a general case, then we'll come back and it makes more sense. So general case. What is the condition for this system? So that its x and theta are decoupled. So let me draw the system. This one is K1, this one call it K2. This time our center of gravity is in some arbitrary number. So this is G. And let's assume the distance from the two sides are A and B. Let's see. So this is A and this is B. Okay, so remember for most shapes and natural frequencies and these couplings, decoupling, you only care about the stiffness. The dampings, they came to play, they're just part of the game. Now then we can calculate the damping natural frequency. So I'll let you to draw these things. All right, so we're going to find the conditions that make this system in a way that if we choose x and theta, they will be decoupled. Right, so it's a bar, the mass, let's say M, and the total length, let's say, is L. Similar to the previous one, but this time it's not symmetric. Like always, we start with free body diagrams, right? So, and I know my variables, similar to the previous one, are x and theta. So I'll choose my x and theta, and I try to draw the free body diagram for this one. So my forces then will be for this spring and that spring. So this spring will be K. It's going to move by X minus A theta. And this guy is going to be K2 X plus B theta. Okay, so that's my free body diagram. I take the moment about point G equal to I bar theta double dot, and I take the forces equal to mx double dot. Two equations similar to the previous one. Again, I'll leave it to you to do all the hard working and the math. At the end, you will get to the stiffness matrix, which you wish it to be decoupled. All right. Maybe we should go through the pane and write it down. Let's write it down together quickly. All right, so let's take the first one. I'm gonna get minus k a x minus a theta and minus this one will be a2. Remember our positive direction was that direction. So it is going to be positive and this one is going to be negative. minus K2B x plus B theta. So these are the forces, and this one is I bar theta double dot. Sum of the forces in X, so I have minus K1 X minus A theta, and K2 X plus B theta equal to M X double dot. And let's stop, check, make sure that we are correct. So remember, we have these two forces. We take the moment about point G and our positive directions. That's for rotation, and upward is for X. So this is our X and theta. Seems to be correct. Now let's put them in a matrix format. So I'm going to have I, and over here I'm going to have M 0 0 theta double dot X double dot. Be careful about the order. This time I write the order first theta and then X. So for K, let's see what we have. I'm gonna have K1 and K1 A squared theta, and I'm going to have K2 B squared theta. So for this guy, I'm going to have K2B minus K1A. K2B minus K1A. I should have calculated before. So K2B minus K1A. But you guys can check, make sure. So, and this one is going to be K1 plus K2. Theta and X. Hope it is correct. I'm going to give you a moment. I know always there is someone who checks these things and finds a mistake. Yep. The stiffness matrix, we have theta and X, right? So, okay, let's check this one. This is K1 A squared theta. Oh, yeah. No theta here. Thanks, Michi. I told you always there is someone who check, find a mistake here. The rest are correct? Yeah.
Not a mistake, but I was wondering, so I, in this case,
We transfer axis parallel axis here. Yes, you can use that one if, let's say, the shape that I have here, right? If it is a regular shape and the question gives you some information for, let's say, the center point, yes, you can use the transfer answer for finding the I bar. But let's assume this shape is not a bar, some random shapes, and its center of gravity is G, and you know I, or I bar. You know, actually, people do this sort of test to find I bar. This is what actually you will do in your experiment, lab experiment. And by the way, for your lab experiment, somebody asked for the string So dental floss is a good thing to use. You can also buy, I guess, strings from some maybe, I guess, dollar stores. But the best person to ask question if you have any technical question or any detailed question about the lab is your TA. His contact is on Canvas because he is the one who did the actual test, make the changes. So he knows everything. I don't. So if you run into any issue, ask him. Probably he ran into that issue before and he can answer you quick. So let's get to this one. We want, like the condition, the question asks, we want X and theta to be decoupled. And we know there are conditions for decoupling, right? So already my mass matrix is decoupled. The main diagonal, they are I bar and M. And looking at the stiffness matrix, it's not diagonal, but luckily they are the same. And we know in order to have them decoupled, we need to set them equal to 0. So for decoupling, all I need to have is these two guys, set them to 0. So K to be equal to K1A. And that's the condition. If I have that condition, what will happen? This system will be decoupled. And what is this condition? If you look at them, what it tells you. K1A is equal to K2B. It's just a balance, a static balance, right? Static balance, that rotation, the moment about G is 0. K1A, K2, B, like a static balance. So something to know. And why this is useful? Sometimes in design of things, let's say you have a system, you design it, you want it to only move ups and down when you excite it. You don't want any rotation. Because when the system is decoupled, it has this condition. Let's say if I move point G up, if I move point G up and release it, it's just going to go ups and down, no rotation at all. So I repeat it again. When I have these conditions, K1A is equal to K2B, it means X and theta, they are decoupled. They are not going to interfere with each other. So physically, what does it mean? It means if I move this bar, this mass up without any rotation and release it, it's just going to go ups and down forever with no rotation. Now, if I just rotate it without any moving the center of gravity ups and down, if I just rotate it and release it, it's just going to swing, rotate with no moving ups and downs. Right? And it is useful in many designs. Sometimes in a design, we don't want any rotation or we don't want any ups and downs. If we satisfy that condition, we will get to that. And that's sort of the meaning of decoupling. So one last thing here. This X and theta, when they are decoupled, what does it mean? It means they are principal coordinates, right? And you learn how to find principal coordinate. But remember the last sentence that I said last lecture? Not sure it was the last sentence, but I remember I said principal coordinate, they don't have any physical meaning. Just mathematically, we make our stiffness and mass matrix independent. Sometimes, like this example, where the actual coordinates, they happen to be the principal coordinate, they have some physical meaning. Okay, similar to this one. Right now, X and theta, they are principal coordinates. It means they make our mass and stiffness matrix decoupled. And physically, we know if we just move one of them, disturb one of them, it's not going to have any effect on the other one. But let's say in any other conditions, if I don't have this Ka equal to K2b, any random system, all right? Listen to this part. If any random system without having this condition, if I just move it up, all right, without any rotation, and I leave it, does it going to go ups and down only? No. It's going to also create some rotation. So the movement up is going to have an effect on rotation as well. And it can be shown looking at only at the equations. So that's about this one. Any question for this? Are we good? Good. So why this one is useful for your project, I will get to it in a moment. Please solve example 24. It is easy, but interesting. And please do it yourself. That's easy. I want you to do as a practice. If you couldn't, ask me. Example 25 is going to be very interesting, also easy. Use the Lagrange method, not the Newton method for that one. Easy and also interesting. Do it please yourself. I will post my solution later, but I wanted to do it this weekend, then I thought you should give it some thought. And please, before checking that one, check the card and pendulum problem. Your textbook. First, check this one before attempting to solve this one. There is a nice example, a classic example in vibration, the cart and pendulum one. It is useful for vibration, understanding many things in vibration, and also if you are taking courses in control, it's good also for control as well. And if you have any question, if you couldn't do it yourself, please ask me. And here we have extra pages. That's good. So your project, your course project, I've noticed some of you already started, which is a good thing. Just one thing that, based on the question that I received, you need to be careful. Let's say when you draw the free body diagrams for this one, let's say this is the car. Let's say this is the tire, maybe for like this corner. Hey. Okay, so the coordinate that you have, the question already set them up for you about the center of gravity. You know these things is going to move by x. That's one of your coordinates. You have like a pitch and theta and a phi here. That's a regular car. That's a degree of freedom for that one. And for each tire, you need to select 1 degree of freedom. Let's call this one x1. So when you draw your free body diagram, of course, here you have a spring. The spring creates a force. That force, let's call it K1 is going to be, or K tire is going to be x1 minus, let's call this one the road, minus R. Because the car is on the road and the road creates some sort of displacement, which the question says, shows it by R, and for R you have a function. So that part is easy. The part that I've seen some people made mistake is the force here and the reaction, of course, going there for the spring. And let's say the stiffness of this guy is K. So remember, this is for your tire, and they are different. Tire stiffness. And you can find the value on internet or estimate them. And this K is the suspension or the chassis stiffness. Which again, check internet, you can find some values or estimate them. Doesn't have to be accurate, but something reasonable. For example, do not choose K equal to 10 Newton per meter. That is small. So K here is what goes to the displacement of that things. Okay. So if you look at the corner of this car, so corner of that car, right, I want you to pay attention. The whole thing's moved by X, then it rotates by theta and then phi or phi. So it is X minus, let's look at that distance, is A2 or A1, sorry. A1 theta, and then B1, but B1 is positive. Let's pause and make sure that I got it right. So I have X creates a tension because the whole car moves up. This is what I decided for my X. Then this theta come to play. Theta deflect or compress the spring. How much? By A theta, right? My distance here is A1, so it's going to be A theta. So that's why it is minus A1 theta. What about B, like this pitch angle, phi, this phi rotate that way, moves that point up. And that's why I have a positive things here. So this is for one corner, right? And the same force, of course, goes for the tire. You need to repeat the same things for other corners, and they are all different. Because each corner you have like the situation is different, all right? So if you figure that one, which is easy, then the damping is the same. Remember, in practice, tires usually have damping, but their damping is not that much. You can ignore it. That's why in this picture, tires doesn't have damping, but the chassis, they have damping. And you can find the estimate for a car that you choose. So you're going to end up by a 7x7 matrices. And here you are going to have X double dot, theta double dot, P double dot, X1, X2 double dot, X double dot 3, and X double dot 4. The same for the damping. And then you have your external forces. There is no force for these three, but each of tires, they're going to have a K tire, R, K tire, R, and so on. And you write the equations. So you have all these matrices, and in your tutorial, you can use the same code that your TA used, but you just need to change your mass and stiffness matrices, right? And of course, your excitation. This is actually what in industry people figure out the vibration of a car. The only difference they add, which I didn't want to add that one, but you can, if you are interested, you can add that one as well, is most of the car, they have an engine right here. Not most of the car, all the cars, they have an engine. And the engine, otherwise how they rotate. So the engines, they spin with an omega. That's the speed of the engine. And they have an external force here as well. which that external force is F0 sine or cosine omega t. But for this problem, you don't need to look at the force by engine. Anyway, my point is the actual analysis in industry is like that. And another thing that you need to know is about the road. The road, I showed it by just a function here. And I assume that it is the same for all the roads, but you can check the, I guess, this standard, that's for the road. Depends on the road, if it is on a, let's say on asphalt or on a paved ground or whatever it is, this function, the number can change. And later when we get to the Adams part, I will show an actual model that I built using Adams simulation. Thank you very much for listening. I guess I believe I sent you an email regarding your midterm next week. It's going to be very easy. Just study the material here, the practice examples, and if you run into any question, quickly even during holiday. Have a good day, guys. See you next Monday. And please be on time.